Okay, let's go ahead and get started. Can you see the screen okay? Is it too bright in here? Is that all right? Okay. So I'm recording this. When I had the battery charged in my office, it said I had 2.5 hours, and now it's saying 1.5 hours. I think we'll be okay battery-wise, but I apologize if it cuts off a little bit early. If anybody sees this little light turn red, that just means that the battery in the microphone's dying. Just let me know. I'll switch it out really quick. So thanks for coming. I know not everybody can make the evening review session, so hopefully the video recording is going to be satisfactory. I'll be taking notes in Onenote. You all have the link to that as well from D2L. I'll just take all of my notes under, there's a tab called Exam 1, and then I have a review notebook. I have got the 3 example midterms there as well too. So everything that I'm writing down you should be able to get access to through OneNote. I had sent out a couple emails earlier today. Sorry for the multiple emails, but I tend to get a lot of emails quickly when we get close to the exams. But the 2 big things is that there's a short quiz I want you to take before the exam on Monday. It's going to take you 5 minutes. It's basic stuff like what's the policy for cell phones. Really simple stuff. I just want you to take it. You need to get 100% on the quiz. If you don't get 100%, it'll show you which questions you didn't get correct. So make sure that you get that completed before the exam on Monday. And the other thing is I had a couple questions from a few students about the format of the exam. So there's kind of multiple different examples that I've posted. You've got some that are like all multiple choice, some that are a combination of multiple choice and kind of longer format workout problems. It's going to be some combination of the 2. Your cover sheet says that multiple choice doesn't require work to be shown. I don't give partial credit for multiple choice, but you're probably going to have, I don't know, maybe 4 or 5 multiple choice questions, but the bulk of the test is going to be workout type problems. I just want to make that clear because there were examples kind of both ways that were posted. Other than that, the format of this review session is always just kind of student driven. I know a couple students had emailed about specific questions on some of the example midterms. And so I'm just going to make a list right here. We'll kind of do first come, first serve. We'll try to get through as many topics as possible over the 2 hours. But the first point, the first question I had is on exam B. Do you remember what the questions were that you had?
4 and 5.
4 and 5.
And then also number 11.
Also on exam B, number 11.
A through E.
A through E, okay. All right, so we'll take a look at both of those specific problems. Like I had mentioned on the example exams, I'll talk about the process. I'll talk about what you would need to solve it, but I'm not going to go through and fully solve any of the problems. I wouldn't say that I recycle these questions, but I don't want to have solutions floating out there for questions. Let's just put it that way. But we will talk about it in detail. That's not a problem. I just posted the homework 3 solutions as well too, so those are available if you want to take a look at them. But if there's any specific questions about homeworks, we can take a look at those as well. So what else do you guys want to talk about? Brian? Yeah.
Like, for example, in problem 4 of homework 2, I'm having difficulty like figuring out how the moment is reacting to the force that you're given in like a 3D space.
Yep.
You just use the whole right-hand rule, and I'm going over to class with really quickly.
Okay.
So I'm having trouble like picturing like you have a force goes a certain way. Like how do you actually know where it's?
Yeah, we'll definitely talk about that. You know, sometimes if it's complex geometry, oftentimes the best answer is to use vector notation because that will take care of all the geometry for you. But we'll take a specific look at homework 2, problem 4 to talk about that. What other topics do you want to talk about? Again, the more specific, the better, but we can, talk about some general stuff too. Yeah. Yep. Okay, homework 2, problem 1. Any other topics? Yes.
Homework 3, I believe it's problem 3, and we're finding the distances.
Yeah, and I believe in problem 3, that was the one where the resultant force is acting like way off the beam.
Yeah.
Like you have a 12-meter long beam, and you find that the resultant is acting at like 17 point something meters away. Yeah, we can talk about that. That's a easy thing to look at and say that doesn't make any sense, but it actually is a valid answer, and we'll talk about some real world examples where that's actually applicable. Anything else? Yeah, yeah.
I meant problem 2, actually.
Problem 2, okay.
Problem 3, sorry.
We can talk about both of them if we want to. Okay. And this will be plenty to keep us busy for a little bit, but as we want to add some more topics, we can just go ahead and add them to the list.
Are you going over any of the practice exam problems?
So I'm happy to. So the first 2 topics that we'll be talking about are from example exam B, and we'll talk about questions 4 and 5 and question 11. So I'll talk about them like I mentioned. I'm not going to go through a full solution of them because I don't want solutions to be out there for those problems. But we can talk about them in detail, and that's not a problem.
Can I add one?
Yeah, of course.
It's problem number, I think, 2.
Okay.
I'm going to have to look it up.
Yeah. And do you remember which exam, A, B, or C?
A.
Okay. Yeah. And I'll just put a question mark, and when we get to that point, we'll take a closer look. Yeah.
I'm sorry, Garrison. Through what section of the book is the exam covered?
It's through lecture 6, I believe, is what I said in class. So on the syllabus, it said through lecture 7. We pared it down to through lecture 6. Basically, whatever was covered in homeworks 1 through 3, that's the scope of the exam. So when you take a look at some of the example exams, you'll notice that a lot of those covered reactions, like calculating reactions, like what we're doing right now and what's due for homework number 4. That's not going to be on the exam. So basically everything up to the point where we can start calculating actual reactions. So things like taking a distributed load, whether it's a function or like a trapezoid, and turning it into a resultant, calculating how much moment that causes about a point, cross products, dot products, things like that. That's all fair game for the exam, but we stopped just short of being able to calculate reactions for a system. Okay, well I think this is enough to get, oh yeah, please.
I didn't get that problem number.
Okay.
It was
Number
number 3.
3, okay, great. And like I said, time permitting, we'll get to as much as we can. Okay, so let's go ahead and take a look at example B, problems 4 and 5. And so some of this I'll be marking up the examples up here. Some of them will go back to the review tab and work there. So the example B, I believe example B was like 10 multiple choice questions and then 1 workout problem. Like I said, the balance is going to be a lot more even, probably like 4 or 5 multiple choice, and then the other half of the exam will probably be workout problems. I'm not going to say specifically, but some combination of multiple choice and workout. So here, if we go to problem number 4, okay, so these 2 questions are related to the same figure. So here we're given a wheelbarrow, and we're given the center of gravity and the mass of the wheelbarrow. We're told that it's supported at a wheel at A and then by this handle at B. Assume that there's 2 handles at B, so this would be, I think we had an example or a homework problem where there was like a lamp being held by like 2 parallel cables, or 2 cables that were in the same XY plane. It's the same idea here. There's 2 supports. One's just further into the page and we can't quite see it. Which of the following is closest to the magnitude of the resultant force which the man must exert on each of the 2 handles in order to hold the wheelbarrow in equilibrium? Okay, so this is kind of like solving for a reaction. There's blurred lines between just the general idea of equilibrium and then being able to solve for a reaction. So it's again, somewhat blurred lines. I think that this would be fair game type of a question for the exam. And so let's start thinking about this. Anytime that we've got a system of forces and we're trying to deal with equilibrium, what's like the first thing that you should draw? Free-body diagram. Again, that shows us geometry, that defines our coordinate system, that gives us all of our unknowns in terms of loads or reactions and things like that. So we should really turn this into a free-body diagram. And like I said, on multiple choice, you're not required to show your work, which is one of the reasons I don't particularly like multiple choice. But for the workout problems, you need to show some work, but you don't need to feel like it's got to be a perfect homework problem. I don't have a problem if you want to draw on top of the figure that I've given you. And so instead of drawing like a whole nother brand new diagram over here, we might be able to use this if it's not too crowded for most of our free-body diagram work. Yeah, question?
So for the multiple choice, are we going to be given a piece of scratch paper then to go working out on?
No, I mean, you should have enough space here to do your work, or there should be plenty of space to do your work. I will have extra paper if you run out of space, like front and back on your exam. You can always get some more scratch paper from me, but I try to give enough paper for you to do all of your work on the exam. With the multiple choice, I will point out you will have, it's not a Scantron, but you will have a sheet to transfer your answers to. This way, if you are working through the test and you circle one of the options when you're working it out and you say, oh, that's not the right one, you go back and you change it. This is a place to cleanly record what your final answer is. Just an easy way for me to not have to say, do they mean C or D? There's a bunch of erases and crossed out. This is just a way for you to, at the end, transfer them really quickly here. But to go back to this diagram, we've got this wheelbarrow. It has some mass associated with it, so I need to turn that into a weight. And the easiest way to do that is to apply a weight shown as a force going downwards in the direction of gravity, and then this is going to have some magnitude, mass times gravity. We're given the mass. I expect you to know what gravity is in either SI or foot-pound second system, and so we should be able to calculate that. That's going to be a known value. What else do I want to show here? Let's just kind of expand into what we've been talking about after the scope of homework 3. What kind of reactions am I going to get in this system? Yeah, X and Y forces potentially. How about the A, the wheel at A? What kind of a reaction do I get there?
Normal force holding that wheelbarrow up to that.
Yeah, a normal force perpendicular to the ground. To a certain extent, for a simple system like this, it's relatively easy to basically say what that support is specifically, resisting. But for more complex systems, just divorce completely the idea of this support from what it's actually doing. The math will take care of that later on. So just a cautionary tale. I would try to avoid worrying about the loading in terms of what kind of supports could be here. Just a wheel in a vacuum by itself is going to have a reaction that's perpendicular to the surface that it's rolling on. Okay, and then I'd also heard at this point right here, we're going to have some potential reactions as well too. And what kind of reactions do you think we're going to get there?
Two forces right next to each other at either handle, just drawing the opposite direction.
Yeah, and so if we think of this as like a roller, it would be going vertically up. Is it possible, do you think, like if somebody holding onto a wheelbarrow with their hands, do you think the only way that they could exert a force would be vertically? How else could they exert a force horizontally? It's possible, right? And again, this is where ignoring what the actual loading is going to be helpful, because this is really more like a pin support over here. Hands, grasping a handle, lift it up or down. Obviously with a wheelbarrow, when you're holding onto a handle, you can push it forward, you can pull it back. And so this is really like a pin support here. Now, is it possible that one of those is going to be 0? Absolutely. But when we just draw our unknown reaction forces, we ignore what the actual loading is. We just say, what is it capable of resisting? So I'll call this Bx. I drew it in the negative x direction, but that's fine. If I get a negative value, I'll just know it's the opposite direction. And By, in this case, we can really say like 2Bx and 2By because there's two of them. You could also just say, well, the point into the page is C. And so I'd have a By and a Cy, but because we know they're going to be equal, we can just write them down as 2 times By. Whichever way you want to bookkeep is fine, as long as you recognize that there are two forces adding together equally to represent the reactions at B. Okay, so at this point, we need to go back to the question, and see what it's asking. It says, which of the following is closest to the magnitude of the resultant force that must be exerted on each of the two handles in order to hold the wheelbarrow in equilibrium? Okay, so how could I solve for By and Bx? Yeah, equilibrium equations. So if I was trying to solve for those directly, like which equilibrium equations might you want to run first? How about this? How can I get rid of one of these reactions right away? So summing the forces in the x direction, because what's going to show up in that equation? Bx? Nothing else? What does Bx have to be equal to? 0. So sum the forces in the x direction. There's no horizontal loads. There's no other support reactions that are acting in the x direction. Bx has to be 0. Now, the nature of the support isn't telling us that. The actual loading is telling us that. The nature of the support says I could have a horizontal force. It just so happens in this situation that I don't. Okay, so Bx is going to be 0. Okay, so I've gotten rid of Bx. That's great. What do I do now? If I sum the forces in the y direction, that's a natural next step. But what's the problem going to be? Two unknowns. So what do I need to do instead? Sum the moments. If I'm trying to solve for By, or the 2By in this case, where do I need to sum the moments about? Well, if I sum the moments about B, does By show up in that equation? No, it doesn't cause a moment about B. It's coincident to B. Okay, so if I can't, what if I sum them about here? Does that help? If I sum about G? Then I get two unknowns, exactly right. I'd get AY causes a moment about G, and BY causes a moment about G. So I've got to sum them about A. If I sum them about A, this point right here, wherever we have the geometry for, I think point A makes the most sense. If I sum the moments about A, I know the moment arm for the gravitational force. I know the moment arm for 2By. Can I solve for By? Absolutely. There's only one unknown. And then based off our discussion of our first equilibrium equation step, getting Bx equal to 0, that takes care of question number 5, which asks you about the nature of the direction of the reaction at B. So again, this is support reactions, right? This is homework 4. This is post homework 3. But it's covering the same equilibrium topics that we've talked about in terms of things like particle equilibrium. It's the same kind of idea. Now we're just dealing with moments. So again, probably not, I said fair game for the exam, but looking at this a little bit more, probably not, because this really is a support reaction type question. But I think the concepts are still really valid. Okay? Any more questions about that, Rachel? Good to go? Okay. Yeah, so let's go ahead and we're going to go to, oops, didn't want to make a new page. We'll go to example 1B, question number 11. Okay, so question number 11, it's a similar situation where this is going to be asking us to find support reactions, but again, for everything that you're doing in terms of simplifying down multiple loads to a structure into like a single moment, a single force, it's the same kind of procedure. It's just that we don't take it to the extra step of drawing the support reactions and everything else. But I think, again, similar concepts, forces, moments, equilibrium, it's all still in a problem like this. It's just that for the scope of exam 1, I'm not going to ask you to find the reaction at this pin at A and the reaction of the journal bearing at B. But let's talk about the problem, because the more fresh it is in your mind, the more kind of confident you're going to be with the same concept on the test. So here we've got this crane system. We've got this sliding boom, this crane, and supporting some sort of weight. And we've got the structure, and we've got this beam CD. And it's asking us to assume that the weight of the structure is 5.8 kips. I'm sorry, the weight of the container is 5.8 kips. And this value x is 6 feet away from the column. Determine the support reactions at A and B. So you can see this is where I can easily vary the values on your exam, like I've done on homework 1 and 2, but not on 3 and 4. I can basically say, assume this weight is 5.8 kips for one of you, 4.7 kips for another one, etc. But we can basically, for part A, say this is 6 feet, and the weight of this is 5.8 kips. Determine the support reactions at A and B. So just like with the wheelbarrow, what's step number 1 going to be? Freebody diagram. And so the geometry is essentially shown here. We have all the geometry I think that we need. This, I wouldn't call it a red herring, but a lot of students get caught up on this cross brace right here, thinking that it's going to affect somehow the answer to this problem. That's, again, I wouldn't call it a red herring, but I would say this is inconsequential as far as the support reactions are concerned. Do you have a question? Yeah.
That's exactly what I want to ask. Doesn't that change the moment because it shifts the load somewhere else on the beam?
So it changes the internal moment in the beam. It doesn't change the moment caused by this weight as it gets applied as forces at A and B. So you're absolutely right, but you're like one class ahead, kind of, well, maybe half a class ahead thinking about that, because we will get into what is the internal moment carried by this beam. But at this point, all that we care about are external reactions. But you're right, it does affect the system, but not the overall reaction to A and B. So it's true to say that there is an effect by this brace, but the effect is not part or not considered when we look at the reactions at A and B. Okay, so pin at A, so what kind of a reactions should I draw there? Yeah, forces, orthogonal, it makes sense to put them in the vertical and the horizontal direction. I'll go ahead and give myself a coordinate system here as well too. And then B is a journal bearing. It says smooth collar. In 2 dimensions, it's the same idea. It's free to slide vertically, but it can't slide or translate horizontally. So I will get a horizontal reaction as well too. All right, so how would I go about solving the reactions at A and B? Is there an equation that I could run to solve for one of these really quickly? Yeah, which one could I solve for really quickly? Well, if I sum the moments about A, the only unknown I would get is Bx. I could solve for that. One equation, one unknown. That works great. What else? Sum of the forces in the y, I only get AY. It singles that out. I can solve for that directly as well too. And then how could I solve for AX? I could either sum the moments about B, because that gets rid of AY and it gets rid of BX, and I could solve for AX directly, or once I've solved for BX already, I could then just sum the forces horizontally and find out that AX and BX have to be equal and opposite. All right, so again, reactions outside the scope, but summing moments, things like that, it's the same idea. Now, part B, it's basically the same question. The geometry slightly changes, and it tells us to assume that beam CD has a uniform weight of 1/2 a kip per foot. So at that point, we've got the same free body diagram. This turns into 8 feet. And then I have to apply a uniformly distributed load to member CD. And that's simply going to look just like we've been dealing with on the recent homework. Distributed load, but it's not defined by a function. It's just a rectangle, which is great. And I can't remember what they said, 2 kips per foot or half a kip per foot or something like that. If I know that the intensity is half a kip per foot, that's just the height of this rectangle. And some of the mistakes that I saw with this problem on the exam is that some students only applied it from point C all the way to where the crane was, but it tells you pretty specifically it's the weight of the entire beam CD. And so what would I do to make this a complete free body diagram? What should I do with this distributed load before I start running my equilibrium equations? Yeah, replace it with the resultant, exactly right. There's my resultant. The magnitude of the resultant is equal to what? Yeah, the area here, what's that area going to be? Yeah, so just 5 kips, right? 10 feet is the width, 0.5 kips per foot is the height. You multiply them together, the units work out, and we get 5 kips would be the resultant. Now, the location of the resultant is simply defined as acting where? Yeah, in this specific case, half the width, but in a general case, it's just going to be at the centroid of the area defined by this distributed load. So rectangle's easy, triangle's pretty easy. Right, so those are the shapes that we're generally going to be seeing, but if we had a function, we would have to use our first moment of area function that we talked about, and what you had as the last problem on your homework number 3, you would have to do some integration to find what is that location of the centroid horizontally. But for rectangles, triangles, life's pretty easy, right? Okay, that's the only kind of wrinkle that we add in subpart B. Subpart C. Oh, here's a good one. Based on the loading in part B, determine how much column AB would rotate if the support at B behaved as a horizontal linear spring with a stiffness of 10.2 kips per foot. Okay, so I'm going to redraw it here just a little bit. We keep a pin at the bottom. We have our distributed load still on beam CD. We've got our weight of our crate as well too. And the only difference really is that now at the top at point B, instead of having what's essentially a roller support, we get a spring, a horizontal spring. Is that going to change my reactions? How's it going to change my reactions? How about this? What if we had a simply supported beam like this versus a beam that has 2 springs on it? If I apply this load anywhere, I'm going to get the same vertical reaction at this roller on the left that I would in this spring. I'm going to get the same vertical reaction on the right as the compression force carried by this spring on the right. A spring in a statically determinate system, which is kind of our purview in this class, doesn't redistribute the forces at all. My equilibrium equation is going to be exactly the same whether it's a reaction underneath a roller or a reaction underneath a vertical spring. So the good news is this behaves exactly like part B up above. I get the same reaction forces. The only difference is that once I get the force carried by this spring, I can then calculate what? If I know how much force this spring resists, what else can I calculate? Yeah, how much it's going to move. And so we talked about this a little bit in class, and again, outside the scope of exam 1. But if I knew that this resisted, let's say, 5.1 kips horizontally is what this is carrying, let's say, in tension, how could I calculate how much it displaces? I just divide it by K. And so 5.1 kips divided by 10.2 kips per foot, it's going to displace half a foot to the right. So the springs are really just there to allow you to do something extra with the forces that you calculate. There's rotational springs as well too, but mostly we just deal with the translational ones. Okay, so this is another good question because this is not just related to reactions, but this is related to just kind of our definition of what a moment is as well. So this is more of a qualitative question that I would want you to explain your reasoning in like full sentences, complete sentences. Based on the loading in part B, qualitatively describe how would changing the height of the beam CD, shown as 9 feet, change the reactions at A and at B. So let's go back up and take a look. This beam CD is 9 feet basically above the ground, or 9 feet above this pin. If I were to move this beam upwards, would that change my reactions at B and at A? Yeah.
I don't think it would change that B, but at A it would change your length of the arm. And that would affect the moment.
Okay, so let's draw what those arms are. So the moment arm you're talking about is from here at A to where? To the beam?
C.
To C. Okay, so that distance right there, I'm just going to draw it here. Okay, so we define like a moment arm as the perpendicular distance between our point of interest and the line of action of a force. Okay, so the lines of action of the forces that we care about, so here is BX is going horizontal, that's perpendicular to this moment arm. Right, but this distance, A to B, isn't changing. We're just increasing the height of CD. AX, I mean, that's right at point A. That can't affect the moment about A. The force of this, the weight of this crate, is vertical. And again, for this problem, we don't have to worry about the distributed load. But even if we did, that has a vertically oriented force on it. So BA, this distance is not changing, just the height of CD is. So what are the actual moment arms that we care about? Let's still focus on like moments about A. Doesn't really particularly matter, but which direction is the moment arm? Like from A to the forces that are going to cause a moment about A? Well, one of them is fixed, AB, and then this horizontal distance would be the moment arm for this vertical force. Even if we still have this force, its line of action goes down here, so its moment arm is going to be horizontal. If I move beam CD up or down, it doesn't change that horizontal distance. And so we're going to get the same forces because the moments caused by these vertical weights, the up and down weights, are not going to change, let's say, the moment about A or the moment about B. It's not going to change the equations that we use to solve for the reactions at A and B.
Will it change the reactions though?
Well, so let's think about that's basically the same thing. The supports at A and B, the reactions at A and B. What about the, so sum the forces vertically, AY is not going to change. Right, just moving this beam up isn't changing the magnitude of any of these forces. So moving it up AY, we know for sure is not going to change. Just moving the beam up, we're not adding any weight to the system. Okay, let's sum the moments about B. If I'm summing the moments about B, AX times 12 feet, that doesn't change. 5.8 kips times 6 feet, that doesn't change. Right, it's 6 feet higher up, but it's still a horizontal distance. So it's not going to affect the reactions. Now again, the same discussion as this brace, will it affect, let's say, like how much this column is going to bend or like the stresses on that column? Absolutely. but that's not what we're talking about. We're just talking about the reactions at A and B, and we'll get to the discussion of what's happening internally in these columns, in these beams, in these braces later on, both in this class and in strength of materials. But the actual reactions itself, all that we would need to do is actually go back and just look at our equilibrium equation. And so I'm just going to write it out. I'm going to say the equation that I use to solve for AX is the sum of the moments about point B equal to 0. And that equals AX times 12 feet minus 5.8 kips times 6 feet. That's the equation that I use to solve for AX. What in this equation would change if this beam moved up? Nothing. So again, intuition is something we're going to be developing throughout the class. But even if you're confident of your intuition, just go back and look at the math, because the math is what's really, driving the static equilibrium. And so just going back and saying which of these would be affected. If none of them will be affected, there's nothing else that could possibly change the answer. So, but I do definitely get the thought of, well, it's going to change something in the system. Moving this beam up, it's going to have some effect. Absolutely, you're right. But affecting the supports just isn't going to be what gets affected. Okay, I do like those qualitative questions. Usually with the workout problems, I'll always have at least one qualitative question, so just be prepared for that. Is that everything for question 11? So part E, there's one more question. Yeah, for this question it says, only consider the effect from the linearly distributed wind load shown above. So here we have a wind load W1 and W2, and it gives us the values of the intensity of W1 and W2. Determine the support reactions at A and B due to the wind loading. So same kind of idea as what we've been doing before. We've shown our unknown reactions, BX, AX, and AY. To turn this into a true free body diagram, what do I need to do before I write my equilibrium equations? I gotta do something with this wind load, right? I've got to turn it into a resultant with that force resultant acting at a centroid. And so you have two options here. Some people like dealing with a trapezoid. The equations are in the table in the back of your book if you want to copy them to your note sheet. Some people just want to break this up into a triangular load and a rectangular load, and that is absolutely fine to do. I usually resort to just breaking it up into a triangular load and a rectangular load. The rectangular load is easy because its resultant is just the area of a rectangle, and it's half, acting at half the height. So 6 feet above the ground, area of the rectangle, that's one force applied here. And then the other resultant due to the triangle is going to be 1/3 the distance from the thick end, and the area is just 1/2 base times height, just 1/2 base times height. So I've got two loads here instead of one resultant. Is that okay? Absolutely. I can just run my moment equilibrium about A. I get BX is unknown, but I can calculate this value and location. I can calculate this value and location. So I should be able to solve for BX, no problem, with one equation. Once I know BX, I could calculate AX. And then what's AY going to be in this situation? What do you think? 0. If I sum the forces vertically, it's telling me to only consider the wind load. So I'm ignoring the weight of the beam. I'm ignoring the weight of the crate. And so just due to the wind loading, there is no vertical reaction to A. Now, this is a common way to deal with multiple different types of loads. We might just consider the effects of each of them individually. Just for bookkeeping and kind of organization sake, it's much easier to calculate the effects due to the wind load, get your reactions at A and B, and then just add the effects of the vertical weights and things like that. It's good to kind of keep them separate. Sometimes we need to do that as well too, because we then increase, say, the wind load by 40% to deal with uncertainty. We increase like the weight of the crate maybe by 70% because there's more uncertainty in what the cargo weight might be, something like that. But it is common to deal with them separately. So again, another kind of conceptual snag point here potentially is that you see a crate, you see this beam, and you know they've got some weight because you've already dealt with weight before, and then it's just a matter of being really careful about the call of the question. Again, I'm not going to try to pull one over on you. I'm not going to try to sneak something in and be sneaky like that. But if I clearly call something out, you want to make sure you read through that carefully. A couple other things, I've been meeting with some students just talking about general test-taking strategies, and I guess this is as good of a point as any to talk about some of that. Stuff like that where reading this once through, it might be easy to miss one of the provisions of the question. And so I actually often recommend, as soon as you get the exam, reading through the whole thing without trying to answer any questions, or reading through the whole thing and just writing down maybe what the governing equation is going to be. And then going back and then actually working on each of the problems. Because you're in a rush, you feel time constraints, things like that. It's easy to skip over some critical phrasing in the question or to just misread it. And so I often like reading through the exam. Maybe a question like this, I could simply just write down the equation for the area of a trapezoid or something like that. And I know I'm going to need that equation. I'm not going to plug in any values yet. I'm just going to write in from my note sheet what the equation of a trapezoid is or the centroid is. And then I'll do that same thing for the next subpart. And that'll take you 10, maybe 15 minutes to get through that, at which point you've already got some partial work shown. That's going to be worth some partial credit. If you give me some governing equations, even if you haven't plugged in values yet, that's going to show me you know the important equation. That's going to allow me to give you some partial credit. And then when you go back through, you'll be looking at things for a second time. You'll be catching things that you missed before. Or if you want to strategize, you can simply say, oh, I know questions 3 through 5 are super easy. I'm going to get those done really quick. And the other way to kind of budget your time is that it's a 100-point exam. It is a 100-minute exam. So if you look at this is worth 5% of your grade, that means you should spend about 5 minutes on this. So that's a good way to kind of apportion out your time, is you should be spending about as much time on a question as however many points it's worth. Okay, follow-up questions about the concepts we talked about here in this question. Okay, so let's cross that off. All right, so a question about homework 2, problem 4. All right, so homework 2, I don't have that printed out, but I will open that up here. And I'll open up the solutions as well, too. Okay, so homework 2, to get that right, problem 4, then we'll talk about problem 1 afterwards. And Ryan, was this your question? Is that right?
So you basically answered it by just saying, not trying to figure out where it's at in the paper space at the moment at A or B, and just go with the Cartesian coordinates. But that's what I was getting hung up on. Like, how do you try to visualize? If you're pulling down on C, is it causing it to rotate clockwise or counterclockwise? But if you just want us to just take the Cartesian coordinates, then how do you do with that?
Yeah, you should just give, so if you give the moment in vector notation I, J, and K, that gives the direction of the moment in each of those 3 orthogonal directions. That itself has the direction information in it. So a vector response with that moment will tell you the proportion in each of the 3 axes. And from that, you can actually calculate what the angle would be, relative to X, Y, and Z. That's just what is the I component, what is the arc cosine of the I component divided by the resultant magnitude. That's one way to do it. But honestly, that alpha, beta, gamma, those angles, I think it can help a little bit with conceptualizing it, but honestly, when you get into just even moderately complex 3D systems, I think you should just rely on the vector notation, especially for the operations. Now, at the end, I might ask you to tell me what's the overall magnitude of the moment, and then you just use the square root of the sum of the squares. But generally speaking, especially because I think it's also easy to get hung up where there are variable lengths, variable directions of forces as well too. And I think looking at the figure and then seeing if that even agrees with what the relative signs and values you're seeing here are, I just think it ends up causing more problems than it's good for. So that's what I'd recommend. Yeah.
So staying with the moment piece then, with homework 3, so you always said to consider moments going counterclockwise to be positive, clockwise negative. I know on a couple of problems, it showed the moment going clockwise, but it gave a positive number. So if we're doing calculations, if we're on an exam, and we see the positive number going to the right, should we put it on paper as being negative?
So that's that.
Go with what it's given us on the question.
Yeah, so that's a good question. So let's talk about that, because I think that is a valid thing to talk about. So let's say that we're looking at a system that has, let's just say 5 feet, 5 feet, and we've got a point load of 10 kips right here, and on the right-hand side we have a 10 kip foot moment. And maybe the question asks, take the loading shown on this system and give the equivalent resultant force and couple moment at point A. So if this was like my free body diagram, we traditionally show X to the right and Y positive up, and that would mean that counterclockwise rotations are what we would consider to be positive. Now, this coordinate system is our traditional coordinate system, and you are free to rotate it any way that you want. It will not affect the final answer, because in your final answer, when you show the resultant force and moment here, you're going to show them with the actual direction that they're going. So let me just kind of show by example here. If I use this coordinate system right here, and I was trying to find what the equivalent moment resultant is at A, if I'm using this convention, counterclockwise is positive, I would get negative 10 kips times 5 feet minus 10 kip feet, or in other words, I would get negative 60 kip feet. What that tells me is that the actual direction this is going to be clockwise. That's what it's telling me, because I'm assuming positive is counterclockwise, so if I get a negative value, it's actually clockwise. So as long as you're telling me somewhere what the actual direction is, or I mean, even just showing me what your convention is and giving me the value, that's going to be good enough. I think the cleanest way to give me your answer for something like this would be to take the beam. This is what I showed on the solutions for the homework as well too. I would simply show at point A, I would show a clockwise moment with a positive magnitude here. So you're absolutely right. When I sum the moments up based off this convention, it's going to show up as negative. But this is just a vehicle. I'm sorry. This coordinate system is just a vehicle to be consistent with the signs in this equation. So look at what happens if we do the opposite. If I were to do, I'll just call this x prime, y prime, and I'm going to say this is negative now. When I sum my moments to calculate the resultant moment, I'm going to say clockwise is positive, which means I get positive 10 kips times 5 feet plus 10 kip feet. I get positive 60 kip feet. but positive 60 kip feet, assuming clockwise is positive, is the exact same thing as negative 60 kip feet, assuming counterclockwise is positive. So both of these, the way that I like to show them is, regardless of what my sign convention is, in parentheses, I will show the actual direction that the moment is going. Same thing with forces as well, too. Your coordinate system, I wouldn't call it arbitrary, but it won't affect the final answer. You're just responsible for showing me in some manner, whether it's in like parentheses like this or on a diagram what the actual direction is. You just need to show what the actual direction is, and that's what I care about. Now, when it comes to internal forces and resultants that we'll get to in a couple of weeks, that's going to change. Well, I'm sorry, that's not going to change. We're still going to be able to change our coordinate system like however we want, but we will have what's called like a sign convention that tells us the assumed direction of forces and moments inside of a beam. But for now, you could theoretically, you could make this 45 degrees if you wanted to. As long as you can show me the actual direction, that's what I care about. Okay, so let's go back to our list here. So homework 2, problem 1. So this definitely caused a lot of problems. It was similar in a lot of regards to the hanging candelabra or chandelier, whatever it was, that we talked about in class. But let's take a look at this and relive the magic. So let me take a snapshot, and we'll just copy this over and put it down below. Okay. So there's 2 parts to this problem. One of the parts requires you to iterate. I know I talked to a couple of students that said they were able to solve it without iterating, but I haven't talked to them since the solutions have been out, so I'm not quite sure if that's still the case. But I don't know of a way to solve this without iterating. The first part of this problem gives you a force, and it asks you to calculate how much deflection D point B undergoes. So point B in the unstressed condition is, or these springs are oriented vertically, and then as we apply a force to it, it begins to displace to the left, and we're trying to figure out for a given force F at equilibrium, how much does this point B displace? And so for the most part, that's really dependent on, number 1, how much force you've got, and then number 2, how stiff these springs are. If these springs were very, very flexible, you could potentially, extend it quite a bit under a relatively small amount of force. And so what should be our first kind of point of recourse here? What's the first thing that we should start looking at if we want to put numbers to this system? Free-body diagram. That's almost always going to be the answer to any question that I ask. It's always just going to be free-body diagram no matter what. So this is like a particle equilibrium type problem where we can just make a section cut around point B, look at all of the forces flowing in and out of there, with the caveat that we will need to look at the deflected geometry of at least one of the springs to be able to relate that distance D with how much this spring is deflecting. And why do we care about that? Why do I care about what the final distance of this spring is? I haven't had to care about that before. What if I knew what the final length or the deflected length, the change in length of this spring was? If I knew what the change in length is, what can I then calculate? What the force is. Because there's a direct relationship between displacement and force, and that's what our Fs equals K times delta is. So again, this is where we're bringing in some force deformation relationship and kind of marrying it with statics to be able to solve these more complex systems. So let's just go ahead and look at that free body diagram of joint B. And so we've got a particle, just a single point in space, and I know that I've got some force acting at point B. I think in the solutions I say F sub A, because it's meant to be the force for subpart A, which is a little bit confusing. It doesn't mean to be the joint at A. So just keep that in mind when you're taking a look at the solutions. F sub A means the force given for part A, but it's actually applied at point B. It's a little bit confusing just bookkeeping wise. And we're going to have some tension in each of these springs. And I'm going to go ahead and put our traditional coordinate system down here, X and Y. We don't really need moments for this, but I'll draw the assumed positive rotation. Okay, so I need to look at this a little bit more in a detailed manner because at this point, I know I'm going to need to look either in the X or the Y direction, but I need to break up my tension forces into their X and their Y components. So I'm going to bring in what we call like a straw man, like an intermediate value that we don't really need, but it's going to come in helpful in a bit. So here theta is simply the angle between the tension resultant and horizontal. And so I could now say that tension in the X direction equals T times cosine of theta. And I can say that the T in the Y direction equals T times sine theta. And we'll have the same thing going down. And I've written both of these as just T sub X. You could have written them as separate variables, but if we were to sum the forces vertically, I could find out really quickly that they'll have to be equal to each other. So I'm just drawing them all as T, basically due to symmetry. Okay, so again, summing the forces in the Y direction, because we've basically replaced these angled tension resultants. If I sum my forces in the Y direction, all that I get is that Ty going up, Ty going down. I just know that they have to be equal to each other. All right, so that's basically what tells us symmetry is at play here because they're acting in equal and opposite directions, and those are the only forces applied. So summing the forces vertically just tells me T equals T, which is not a surprising result. All right, horizontally, if I were to sum the forces in the X direction equal to 0, I get negative that applied force in the negative X direction plus 2 times T times cosine of theta. All right, so here I don't know the magnitude of T and I don't know the direction of T yet either. And we don't even have D in this equation yet. All right, so I wouldn't say life's not great, but we don't have a lot of information yet. So I need to start bringing in some other equations to get this over here in terms of that force D. So let's go ahead and just look at a diagram of that stretched spring by itself. So if I have that stretched spring, it has a width D, or horizontal distance D, and what's the original vertical distance? It's just given as like L naught in the problem. And I believe you're given the value of L naught as well too. And so I know L naught, I don't know D yet, but can I represent what this hypotenuse is? What would it be? Right triangle, right? D squared plus L naught squared, square root of that quantity. Square root of the sum of the squares, Pythagorean theorem. I can represent this, not a problem. Okay, so is there any way to take this geometry here of this, again, remember, right triangle, and can I substitute anything in this equation with maybe some values out of this right triangle? How about this? This is 90 degrees, right? What's this angle? It's not going to be 45. That's a good guess. A good place to start to iterate maybe. What do we call it in our free body diagram? Theta. Okay, if this is theta, what's another way to say cosine theta? What is the definition of the cosine of an angle? It's the ratio of the length of the adjacent side to the length of the hypotenuse. So cosine theta equals d over d squared plus L squared, L naught squared, that quantity square root. All right, this can go into this equation and completely replace cosine theta. Now, that's good because I need to solve for d. I needed to get that in this equation somehow. I already know L naught, so I'm bringing d into the equation, which is great, but I still have an unknown, which is t. All right, so just to be clear, this goes here, but I still got t, and I don't know t yet. How do I calculate the tension in a spring? What's another way to calculate the tension in a spring, other than just statics? Can I relate the tension in the spring to maybe how long it is? Kind of. I mean, how long it is the final length minus maybe the original length. What would I get if I took this final length and I subtracted this original length? The change in length. And we just happen to have an equation that tells me the relationship between the change in length of a spring and the force carried by that spring. T in this case is just the force in the spring. So I can take this equation and solve for the force in that spring based off of my geometric diagram here. So let's go ahead and do that. Let's just say the tension in the spring equals the spring constant times the change in length. But how can I represent that change in length? Final length, original length, subtract one from the other. So radical d squared plus L naught squared minus L naught. That goes into the equation there. So at that point, it just gets a little bit ugly in the sense that I get the force in member B equals 2 times this quantity times this quantity. But there's only one unknown, right? In this whole equation now, d shows up 3 times and it's the only unknown. Now the problem is that I can't easily simplify it down to get d by itself on one side of the equation. I wouldn't call it locked in a radical, but it definitely is really difficult to get it out of the radical and not affect these other terms. We have d to different powers, and as a result, I need to guess and check different values of d until this equation is satisfied. So just to be clear, I need to run the equation FB equals 2 times k times the quantity d squared plus L naught squared minus L naught times d divided by radical d squared plus L naught squared. I need to make this equation have the left side equal the right side, and so if I were to plug in a guess a value of d, maybe put in the value of L naught, assume a 45-degree angle, see if the left side equals the right side. If it doesn't, try a bigger value of d. If you're getting further away, then go back and try a smaller value of d. Another common way to deal with this is just divide both sides by f sub b, and that way you're just trying to find the value closest to 1, and that's another way to do it. So again, for the homework, an iterative process with a longer kind of format, having to remember trigonometry, unit circle, stuff like that a lot more clearly. I think this is a good homework type problem. You shouldn't expect to see something as complex on the exam. But part B, right, part B, they give you the value of D, and so you know what the geometry is of that spring. Part B of this problem is deterministic. You can solve directly for the force, and so in that regard, part B of this would be more kind of a fair game for the exam. And so just to remind you, in part B, I give you a value of D, and I ask for what is the force that's required to cause that displacement d. And so could I easily calculate theta in that situation if I know what d is? Absolutely. I know the width of the triangle. I know the long leg of the triangle as well too, so I could calculate all of the angles of that right triangle. So if I knew what theta was, then it's basically just this free body diagram, and then I would also be able to calculate what the, I'd also be able to calculate the length of this spring. From the length of the spring, I can calculate the force in the spring, and then I just go back to my free body diagram. No iteration required. That would be, at least one less step and no iteration. So that would be, again, more in line with a potential question for an exam. All right, follow-ups about this problem. Okay, let's go back to our list. Okay, homework 3, problem 2. And like I mentioned, I posted the solutions right at 6 o'clock for homework number 3 before we started this. Okay, and homework 3, problem 2. Okay, so problem number 2 is this overhang beam. We have a pin and a roller. To a certain extent, for these problems, we don't really care whether this is a pin or a roller because we don't draw the reaction forces or anything. That's the material after what we're going to cover on the midterm. So here I've got 3 applied forces and an applied couple moment here. And I'm asked to replace all of the loading, again, just ignoring the support reactions, just take all of the loading, the 3 forces and the 1 couple moment, and replace them with a single resultant force acting some distance from point B. And then the other would be a resultant force and a couple moment acting at point A. So when we say resultant, usually what we mean is the vector sum of 1 or 2 or more vectors. So you can think of it in the sense of all of these force vectors are going to have their I and j components added together, and the result in I will be the magnitude of the new vector in the I, add up all the j direction, the y direction, that will be the new vertical component of that force. And so part A is relatively straightforward in the sense that really all that I have to do for the resultant force in the y direction, just sum up all of these applied loads forces in the y direction. So in your free body diagram, and I think what I did in this example is I took the inclined loads, and on my free body diagram, before I started doing my equations, I broke these up into the x components and the y components. Again, a lot of people skip that step, and a lot of people are fine skipping that step, and a lot of people will just look at the given figure up here and say, oh yeah, cosine 60 for the horizontal, sine 60 for the vertical, and they go over here and they're going really fast and they do the same thing. They say, oh yeah, I remember 30 degrees, or it's similar enough to 60, or you could mess up the sine and cosine. A lot of things could be an easy mistake to make. If you were to do that as like an intermediate step where you would be able to label the force magnitude on a diagram, it would be a quick way to kind of check and say, oh, if the horizontal component here was 606 and the vertical component was 350, and I drew them relatively to scale, I could probably pretty quickly find or identify that mistake. So again, on the homework, I understand you have more time to do stuff like this, but being explicit about your intermediate steps, I think, is a good way to not make those easy transcription or sign mistakes that are so common. So either way, if I'm going to be adding up all the vertical components of the forces, all of the horizontal components of the forces, I should break them up into those respective components. And then now for the vertical components, I just add up 389.71, which is just 450 sine 60, add all of the 300 newtons, add the 606 Newton vertical component. All of those added together will give me 1,296 newtons. Here I said negative because my y coordinate was shown positive going upwards. But just to be clear, in parentheses I identified the true direction being in the downward direction on the page. Do the same thing for the components in the x direction. Here I have 225 newtons pointed to the right, 350 newtons pointed to the left, and so my overall resultant is 125 newtons pointed to the left. Oftentimes you'll have to also give the magnitude and the orientation of that single resultant. If it asks you for a single resultant, you would need to take the x components, the y components, calculate the overall resultant, and calculate the angle. And I had a lot of questions about this for homework 3, how to show the angle. I'm calculating the angle from the x direction going positive counterclockwise, towards the y direction. I calculate negative 95.5 degrees here. And so I just show that that's going to be in quadrant 3. That's what this little angle symbol is for. The other option, just to be clear, is to show the actual beam with all the loads replaced with that single resultant moment. And that way it's really clear what angle you're reporting. So I think the force part of this question is probably the easiest part. And I think that the next part where we're actually calculating how far this force would have to be acting from point B is the more kind of challenging part of this problem. Because I could have easily put that resultant force at point B and given a couple moment that sums up all of the moments due to all of the forces acting on the beam. And this is kind of the first step that we did in class, and I think what people are most comfortable with. To calculate the moment about point B due to all of the loads that we had up above is pretty easy. I just take the vertical force here, multiply it times the moment arm, vertical force here, multiplied by the moment arm, and then I just add on this 1,500 Newton meter couple moment. I'm not multiplying it times any distance or anything else, but I'm calculating the effect that all of these has in terms of a moment about point B. But that's not what this question is asking for. It's saying, instead of putting a couple moment and a force here at B, take that resultant force and move it to the right or move it to the left so that it causes the same moment about point B that all of these forces cause and moments cause about point B. So it's kind of a two-step process. I first need to figure out, well, how much moment is caused by all of these loads about point B, and then I can back calculate how far my resultant force would have to be to cause that same moment. So what I would do is I've already calculated the resultant force, and because it has some x component, it's got some y component, maybe you can tell me which of those is going to actually cause a moment about point B. There's a y component to FR and a little x component to FR. Which of those causes a moment about B? What do you think? If I had a horizontal force acting right there, does that cause a moment about B? Why not? What do I need for a moment? I need a force, right? I've definitely got a force at a distance. Well, I've got a distance. It's whatever this is. What about the distance? It's got to be perpendicular. And so here, the distance from B to this point is in the same direction as this force. That's a parallel distance. That's not going to work. I would need a perpendicular distance from the line of action of that force. And because the line of action of that force goes right through B, there's no moment arm. All right, so whatever horizontal component of this resultant there is, I just ignore that in terms of how much moment it can cause about point B. Just the vertical component of this can cause a moment about B, and I want to figure out how much distance from B I would need so that the vertical component of my resultant causes 1,759.82 Newton meters of moment about point B. I've already calculated how much moment there is about B, and now I'm just calculating how far I would need to move my 1.3 kilonewtons over from B to cause this much moment. We know a moment is just a force times a perpendicular distance, and so I can rearrange that relationship to say, well, the perpendicular distance equals the moment divided by that vertical force. So this equation here is based off the moment about B due to all the loads, which I can calculate really easily, divided by the vertical component of my resultant force, which I calculated up above. Here, it's 1.36 meters. I know the moment is clockwise, and so that 1.36 meters has to be to the right in order for this vertical downwards force to cause a clockwise moment about B. And that's how I know that distance that I get is to the right. Now, I know we changed which problem we're talking about. I had originally started talking about problem number 3, but I do want to just talk about that for a second because I know I do talk a lot about, is there a reasonableness check that you can do on whatever answer you've gotten for a problem? Or we've talked about, like with that spring problem, what's a reasonable like lower bound or upper bound to this problem so we can kind of check our work or figure out where to start guessing. It turns out in this problem that when you're asked to find the location of the single resultant and its distance from O, it ends up being out here. Actually, it ends up being vertical. I drew it kind of inclined, but it's out here and it's something like 17 point something meters. It's off of the beam. And you say, well, that doesn't make any sense. That's not a reasonable answer. And it is simply I wouldn't call it a fallacy, but it is like a fiction that we create that does have some roots in like design practice. I've talked to a couple of students about, and I think I mentioned it in class as well too, that sometimes we'll be looking at the design of, let's say, a footing for a light pole or a building wall or something else like that. And oftentimes it is loaded with a moment at the connection point and by a vertical force at the connection point. And we will often try to figure out, well, where is the resultant force at the bottom that's resisting both this moment and this force? And sometimes that reaction is off of the footing. And there are some geometric limits that basically say the resultant force, if it's outside of the inner 1/3 of this footing, you get penalized because it has a much higher likelihood of overturning. It's more unstable as a result. But all this is doing, like I said, is a fiction that is simply mimicking the effects of this and that distance, that what we call eccentricity from the center of that footing, tells us something both qualitatively and quantitatively about the likelihood that that is going to overturn. So if that resultant is off of the footing, we're going to be penalized a lot in like the maximum force that we can withstand. The other thing I would point out is, what if we had a pipe? Let's say like a pipe column. So maybe this is a pipe like a pipe pile that we're putting into the ground to support a building or a bridge or something like that. And I apply some 100 kips of vertical force, 100,000 pounds of force on this member. Where would I idealize that force as acting? The center. The center, that center is not touching any metal, right? That center is not, I mean, even connected to this column. But that is exactly where the center of the force being carried by that column is. We idealize it on the center because that mimics the overall effect on that column. But really all it's doing is it's just summarizing for us the distributed load, the stress, acting at all of these points along the perimeter of our pipe pile. This is just like a resultant, and it's mimicking the effects of all of this, but it's not physically touching the structural element itself. So it's the same kind of idea, Okay, whoever asked that about homework 3, problem 2, did that answer your question, or did we talk about that enough? Okay. All right, so let's talk about example A, problem number 3. Okay, so yeah, so this is very similar to what Ryan had brought up as well too. This is a question about trying to calculate the moment about a point in 3D Cartesian space based off forces that are provided in vector format. And so here, the only wrinkle about this one really is that we've got 2 forces applied, and so we have 2 different options here. I mean, what is the fundamental equation that's governing how to calculate the moment about this point O due to these forces acting at point A? The moment about O, and I'm going to keep it in vector format because I don't want to worry about keeping track of all of these orthogonal directions using scalars. How do I calculate a moment if I'm given that moment in vector notation? Cross product of position vector from O to A crossed with the force vector, and I could just sum the effects of force 1 and force 2. So I could do this twice. I can do the position vector from O to A that'll apply to both, and then I could cross product that position vector with force 1, get the moment, cross it with force vector 2, get the moment, and add up the i's, the j's, and the k's. Yeah?
So is that the same your resultant force between F2 and F1?
Well, so that's where I'm going next. So that's exactly right. That's really good intuition. What I'm saying first is that we could do the cross product with F2 and that position vector, and then add those results to the cross product of the position vector with F2. I said F2 maybe twice, but you get the idea. The 2 options that I have here are ROA crossed with F1 plus ROA crossed with F2. Or I can just add F1 and F2 together, which probably makes more sense. It's less work. And I could just do ROA crossed with F1 plus F2. You'll get the exact same answer. This is probably going to be less work. Either way, you'll get the same exact answer. Now, just for completeness sake, or just to talk about it, I said ROA here, the position vector from O to point A. That's what I just used by default because I know the coordinates of point A. But technically speaking, what position vector do we need to use in the cross product? Like, what is the general definition of where the position vector has to start and where it's got to end? It's got to start where? At your point of interest, exactly right. And here my point of interest is clearly point O. So this has got to start at O, and where does it have to go to? Like when you say the force, what do you mean by the force? It doesn't have to go to A specifically. It has to go to any point on the line of action of your force. So it just so happens that I know the coordinates of point A, but remember these forces here have a line of action, and theoretically if I was doing this methodology here, I could do the position vector from O to whatever this point is right here. Just keep in mind it's any location on the line of action of the force would be valid for a cross product calculation. That came into play, and you'll take maybe you'll take a look at the solutions for homework 2. Let me point that out just because that's an easy thing to forget. Long homework, wow. Okay, let's look at this pyramid here. This pyramid, this problem is asking us to find the moment acting about this line segment AB due to this force. And so this is a two-step process where the first thing that we need to do is solve for the moment caused by F about some point on this line AB. The moment about some point on that line AB will tell me what is the moment about this specific point, but the next step will be to take that moment and then only keep the portion that's parallel to AB. It's the same kind of an idea. So just keep in mind, and I talk about this in this problem as well too, that our general equation would be, the position vector in the direction, the unit vector is getting messy. Our formula would be the unit vector in that direction AB dot product with the moment vector at point A, I don't know what's going on, or the moment vector at point B. I guess my point is, with vectors, a lot of the time, you can get away with kind of choosing which point you would like to take the moments about, because here I could theoretically take the moments about this point, I could take the moments about this point. Either one has the information about how much of the moment is parallel to AB. So let me just say MA or just like with the formula for calculating a moment, you have some choice about which position vector you use. As long as it ends up on the line of action of the force, that's all that matters. So just keep in mind there is some flexibility with cross product about either where you take the moment, if you're eventually going to project it in a specific direction, or where your endpoint for your position vector is. Just don't forget about that. Yeah?
So when in general does unit vectors become involved when you're calculating moments? Is it just when you're doing about a line rather than about a point?
Yeah, unit vectors come into play when you're trying to project a moment or a force in a specific direction. That's our most common use for unit vectors. And we almost always will use a position vector to calculate a unit vector, but we only ever use them when we're trying to project a moment or project a force in a specific direction. The other time, so let me back up. The other time that we might use them, which is less common, would be to calculate the angle between two different directions. In that calculation, you could use position vectors, but you end up dividing by the magnitudes, and that essentially creates a unit vector. To go way back into like lecture 2, no. Position vector, I don't know if it's in this one or not. The definition of like dot product allows you to calculate the angle, and yeah, this one right here. So our definition of a dot product basically says A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle. You can just rewrite this and you get the cosine of the angle equals A dot B divided by the magnitude of A, the magnitude of B. This is kind of like the unit vector of A times the unit vector of B. Kind of the same idea, but it's more kind of implicit in that situation. So I don't know if it's really the best example, but big picture, usually when you're projecting a moment or a force is really the only time that we use them. Yeah?
So there's three ways we could be asked for a moment. So you can get a moment about a point, a moment about a line, for that stress, and then you get a moment about
Sure, and I guess a moment about the x or the y or the z-axis is basically the same thing as like the moment about a specific line. It just happens to be a lot easier. Yeah.
And so if you ask something about an x-axis, you use like a unit vector.
Well, the good thing about the moment about the x-axis, so let's just say that we had a moment and it was defined as 10I plus 5J minus 12K Newton meters. How much of that moment acts about the x-axis? 10. That's the benefit of the vector notation, is that if I only ask about the x-axis, you can tell right away, because all that I would be doing is doing the dot product with the unit vector in the x direction, and that is simply 1I plus 0j plus 0k. We're doing the same thing as we're doing in that kind of pyramid example. It's just that our unit vector just so happens to be super easy to use with the dot product. In this case, it would be 10 times 1 plus 5 times 0 plus 12 times 0. It would just be that 10. So it's the same idea, but about the x-axis, y-axis, z-axis, you just pull out that vector term. Yes?
Is there, on a slightly different note,
Mm-hmm.
so a moment is the direction of some member cross product with position, or, I mean the force cross product with position.
Mm-hmm.
Why, is there a way intuitively to understand why the moment vector like pops out? I don't understand.
Orthogonal to both of them.
Why?
Yeah, I mean, that's the way that we represent it. I guess another way to think about it is this. So I think that's a conceptual way. That's a good point. Good question. Okay, I think we talked about exam A number 3. So we have time, whatever you guys want to talk about. Yeah, question.
I was struggling with, and I'm referencing this from homework 1 of the 5, but it could just be asked generally, but for a force that has, like, in 3 dimensions, so the axis that has an I, a J, and a K, how do you find the resultant the same way you would find the resultant for a 2D, and then how do you find the directions?
Oh yeah, good question. Yeah, so the answer is yes, you find it the same way as you would in, you said for 3D you would find it basically the same way as you do in 2D. So let's just talk about that really quick. If I had some force vector, and let's assume that it's, I don't know, 10I plus 5j minus 12k, what we used before. Actually, that's, I mean, let's say plus. Let's say it's all in kind of the first out of 8 quadrants there. Positive x, y, and z components. So it's basically ending up like somewhere here, roughly. It's not exactly right. I'll try to make it a little bit more proportional. Let's go ahead and say 2I plus 10j plus 12k. Close enough. Okay, so if I want to find the magnitude, like the resultant magnitude of this force vector, it is still just the square root of the sum of the squares of the I, the j, and the k component. So it's 2 squared plus 10 squared plus 12 squared. That will give me the length of this force vector, the magnitude of this force vector. Now the direction is a little bit different because you have some options here, and it depends on the call of the question. So the 3 different, it can either be 2 angles to describe the location of this vector, or 3 angles. The first one is simply the angle between the x-axis and the force vector itself. So if you were to create a 2-dimensional plane that sliced through both the force line of action and the x-axis, anytime any 2 lines intersect, you can always find a 2-dimensional plane that they would both exist in. So if I were to create a 2-dimensional slice right through F and the positive x-axis, and then I rotated that and looked at it on the side, you know, just brought it up, we could measure the angle in between f and x, and that would be what we call alpha. And so alpha is simply the inverse cosine, arc cosine, of the x component of f, I'm sorry, and the magnitude of that force vector itself. We do the same thing for the y-axis. That gives us beta. And then for the z-axis, it's the same thing, and that's what we call gamma. And they're all calculated the same way. It would just be fy and fz, but still cosine, arc cosine. Now, that's the easiest way to calculate it, and that's what we call spherical coordinates, where we have a magnitude and then 3 angles of inclination from the positive x, the positive y, and the positive z. The other type of coordinates, does anyone remember what they're called? The cylindrical coordinates. The only difference here is that instead of giving alpha and beta, we simply give an angle theta, which is defined as the angle of between the x-axis and the projection of f onto the xy plane. So this point right here that I draw at the very beginning, if I were to go from the end of the force and project down a point and to where it intersects on the xy axis, and then go back to the origination of my force, the angle between the x-axis measured positive towards the y until I hit that projection, that is what we call theta. And so this involves an intermediate step, which I recommend doing it kind of one step at a time. You could do all of it at once, but how about this? F, x, y. How could I calculate the length of this force projected on to the xy plane? How could I get the length of this? Keeping in mind that like this is a right angle up to that point F. So if I know the length of this, if I know the magnitude of F, how could I get down here? Which of those angles would be relevant for that? It's a little tricky, but it would be gamma. Gamma tells me the angle between the z-axis and the force resultant, and you can think of it as this angle right here is also gamma, maybe is the better way to think about it. That angle is also going to be gamma, and so the magnitude of that force in the xy plane is equal to the overall magnitude times what? What do you think? Sine gamma, that gives me this length. And then if I know what this length is, how would I get like the component of the force in the x direction? How could I get the component of the force in this direction? We'll just call that F sub x. If this is a right angle right here, and the angle in the corner is theta, I would say that Fx equals Fxy times cosine of theta. So just bringing in this definition for Fxy into here, I get that Fx equals the overall magnitude of the force times sine gamma times cosine theta. And so if I know Fx, which is simply 2, and if I know gamma, which I can calculate from, the other equation I haven't written quite yet, which would be 12 divided by the overall magnitude arc cosine, I could calculate what theta is. It just gets to be a little bit more complex, but usually speaking, you're just going to be asked for like alpha, beta, gamma. But those are the two different ways to describe the direction of a force vector if you're doing it in scalar notation, either alpha, beta, gamma, or gamma and theta. Cylindrical coordinates or spherical coordinates are kind of the two options. Your book actually does have equations. They just rearranged this to solve for theta. Theta just being inverse cosine of fx divided by f times sine gamma. Okay. Does that answer your question? Okay. I always get nervous when faces go into hands, but okay, what else do you want to talk about? Well, I mean, I'll stick around for a little bit if you guys want to ask any questions one-on-one. Otherwise, like I said, for the example exams, I don't post the solutions, but if you want to post questions to the discussion boards, I'll try to answer them as much as possible. I'll try to answer as many questions as you have before Monday. I can't promise, responses based off other workload and how many emails I get, but I'll try to answer as many as possible. Otherwise, make sure you bring the right calculator. Make sure you turn your phone off, and I'll see you on Monday otherwise. All right, thanks, everybody.